So, already I have discussed various aspects of briefly of course, various aspect of vibration and solution also I have how to use them. I have taken one set of problem and once again I have also mentioned what are the dynamic soil parameters involved for the analysis of machine foundation and how to determine all I have discussed. Now, one more set of problem I will take to understand better. So, let me go to the problem problem number 1 for today's problem. You can see a body weighing 600 Newton is suspended from a spring which deflects 12 millimeter under the load. It is subjected to a damping effect adjusted to a value 0.2 times that required for critical damping. Find the natural frequency of the undamped and damped vibration, and in the latter case determine the ratio of successive amplitude. You can see here that this problem mass is given, mass of the body is given and suppose W is 600 Newton and then you can find out M 600 by G 9.81, which we generally write 600 by 10. Okay. So, it will be 60 and you can see that instead of spring stiffness, when this mass is suspended from the spring, how much deflected is given. From this what we can get actually the load actually is given and deflection is given, actually stiffness, definition of stiffness actually load by deflection. So, that means your load deflection is 600 and your deflection is 12. Okay. So, it will give you 50 Newton per millimeter, is it not? And you can see once again that your K become this, and I know the damping will be equal to C over C c. So, this C is given 0.2 times of C c. So, that means, so it is 0.2 times C c divided by C c, that means damping is 0 nothing but 0.2 and find the natural frequency. So, we have got the spring stiffness. So, let me go to the next page. Your K become K become 50 Newton per millimeter and D become 0.2 and W become 600. And so, your natural frequency omega equal to under root K by M. So, it will be under root K is actually 50 Newton per millimeter square, 50 multiplied by 1000 Newton per meter, and M here actually is 600 and divided by G. So, multiplied by 10 here. So, if we do this 600 by 9.81. So, you get 50 multiplied by 1000 multiplied by 10 divided by 600 under root, this gives you 28.8. It is actually 28.86. Now, your damped natural frequency W d actually equal to omega n under root 1 minus d square. So, d is 0.2. So, 1 minus 0.2 square and that too under root answer. So, that become this multiplied by 28.86. So, it become 28.27. 28.27. This is the question asked actually, natural frequency, damped natural frequency, and also it is asked to find out that is given ratio of successive peak. Okay. So, delta actually equal to nothing but 2 pi d and nothing but ln z 1 by z 2, is it not. So, d already is known, and so your z 1 by z 2 will be equal to e to the power 2 pi d. So, it will be equal to 2 multiplied by pi multiplied by 0.2 this, and it will be e to the power 2 multiplied by pi multiplied by 0.2, that become this 1.256. So, e to the power so it will become 3.51. That means, in that problem where a 600 Newton weight is hanging from a spring and the spring stiffness is not given, instead of that when you hang how much deflection took place, that is mentioned 12 millimeters. If it is given, then from there I got the k equal to w by delta. From there actually it is 600 and this is actually 12. From there I got this, and then from there actually omega n, once k and m is known, then we can find out omega, and damping also is given 0.2, then omega d I can find out, and further last point was asked actually to find out the ratio of successive peak, and we know the ratio of successive peak actually when you put it in logarithm log, that is called logarithmic decrement, and that is actually 2 pi d, and so d delta equal to 2 pi d equal to ln z 1 by z 2. So, z 1 by z 2 will be e to the power 2 pi d, and if you put the damping value here, then we are getting z 1 by z 2 directly 3.51. That means, actually first peak will be 3.51 times of second peak. Okay. So, this is the problem number 1. Let us go to the next problem, and in a cyclic plate load test actually you can see that the pressure applied actually 600 P is actually 20 kilonewton per meter square, and initially was 0.65 meter millimeter, and then finally after rebound on unloading observed plate settlement was 0.60. Okay, then elastic will be delta E will be equal to 0.05 millimeter. So, your Cu will be equal to P by delta E. So, that will be 20 divided by 0.05, and this is millimeter, and so this millimeter to millimeter, so 20 you have to make 1000. So, this way it will be 20 divided by 0.05 multiplied by 1000. So, it gives you 40000 kilonewton per meter cube. Okay. So, this is a very simple problem, whatever I have discussed about the IS code, directly application of that, a particular loading, what is the elastic settlement is given, then the ratio is actually your coefficient of compression, elastic compression. Let me go to the next problem. You can see a mass attached to a spring of 5 Newton per millimeter has a viscous damping device, and when the mass was displaced or released, the period of vibration was found to be 2 seconds, and ratio of the consecutive amplitude was 10 by 3. Determine the damping factor and natural frequency of the system. Determine also the amplitude of motion when a force 3 sin 4t acts on the system. So, here actually you can see spring K is given 5 Newton per millimeter square or 5 kilonewton per meter. Okay. And you can see the period T is given 2 second, which is nothing but 2 pi by omega. So, you from here we get omega equal to 2 pi by 2. So, that means 3.14, omega become 3 omega n natural frequency become 3.14, and then the ratio of the consecutive amplitude was 10 by 3. So, it was delta equal to ln 10 by 3 equal to 2 pi d, is it not? So, ratio of successive peak is this one. If you take log, that is actually delta, and that delta we know this 2 pi d. So, from there I can get d equal to 1 by 2 pi ln 10 by 3. So, from here I will get d equal to 19.16. Okay. Actually, you will get initially 0.1916, but if I put it percent, so it will become 19.16%. Now, actually you have to find out also, let me, so we have done determine the damping factor d already, the damping factor natural frequency already obtained, natural frequency and damping factor already obtained. So, I will clean it, and for second determine also the amplitude of motion when a force of, so F actually is given 3 sin 4 t. So, that means as I have mentioned F naught actually 3 Newton and omega actually 4, and your expression for u equal to F naught by k and 1 over under root 1 minus omega over omega n square whole square plus 2 d omega over omega n whole square. If I do this, and omega over omega n, you can see omega actually 4, omega over omega n equal to 4 divided by 3.14, it is nothing but 1.274, and d become 19 point or 0.191, and if you put this and this in this expression, F naught equal to 3, and k actually already I have shown that k actually 5 kilonewton per meter, k actually 5 kilonewton per meter. If I put all those in this expression, then you will get 3 divided by 5 multiplied by, since both are in expressed in Newton, multiplied by this expression comes 1.263. So, if I put this, then it becomes 0.75 0.758 millimeter. So, amplitude of this vibration, when this system is system will vibrate, then with a force equal to 3 sin 4 t, then your amplitude will become 0.758 millimeter. Okay. So, this is actually problem number 3. Let me go to the last problem. So, this is the last problem. You can see here that plot the frequency amplitude response curve and determine the stiffness and the damping ratio of the foundation soil system for the following data. That weight of the foundation block including machine weight is 8 kilonewton and the eccentric moment is 0.156 Newton meter. Determine the coefficient of uniform compression and damping as per IS 5254. So, this is it is and actually A is missing. So, this is one, and here one data is missing, actually foundation size is missing. So, foundation on which test was conducted A equal to 0.4 by 0.4. So, this data is there. So, this data has to be plotted. So, amplitude versus frequency you have to plot like this, and from there you have to find out resonance Fn, and then 1 by root, and this is xm, and then you have to find out 1 by root 2 times xm. So, 1 point here, 1 point here you can find out, So, like that if I do let me go to the next page, and you can see that if I plot this one frequency versus amplitude, these are actually this is amplitude multiplied by 10 to the power minus 3. What suppose if it is 50. So, if I get 80, so 80 multiplied by minus 3 is the amplitude, and here actually amplitude in RPM. Okay. So, from this actually from this plot I can find out Fn equal to 1650 RPM, or if I CPS if I plot, then it will become 27.5 CPS. What is CPS actually? If I divide by 60, then it becomes CPS. Fn and Xm actually your become 90, and so 1 by root 2 times Xm, that become 1 by root 2 times Xm actually 63.63, and for that somewhere here and somewhere here, and this is if it is F1 and this is F2, then F1 comes as 1580 and F2 comes as 1740. Okay. So, based on that you can find out damping. So, damping will be equal to F2 minus F1 by 2 Fn. Okay. So, that means how much it is? 1740 minus 1580 divided by 2 multiplied by Fn actually is it is 1650. So, if I do this, then you are getting damping value actually 4.84%. This is the damping, and if you want to find out Cu, Cu actually 4 pi square Fn square m divided by A. So, you can see that 4 pi square multiplied by Fn actually here your cycle per second you have to put 27.5 whole square multiplied by m actually 8 kilonewton is the weight. So, 8 multiplied by 10 cube is the in Newton divided by 10 actually taken G, and then divided by area is 0.4 multiplied 0.4. So, this calculation if you do, this calculation if you do, then you may get a value something like 4 multiplied by 8 multiplied by 1000 divided by 10 divided by 0.4 divided by 0.4. So, this value actually 149277 kilonewton per meter cube. This is the value of Cu. So, this is the thing asked for this, and for finding out the damping I can do another way, that is from the peak amplitude I can find out the damping. So, that is another way of finding damping. So, let me try that one, let me remove this one, whatever asked actually as per IS code I have done. Now, let me do the other part. We know that Xm equal to m e into e over m omega over omega n divided by multiplied by 1 by 2 d under root 1 minus d square, or it can be at m e into e over m multiplied by 1 by 2 d. So, approximately if d is small, this approximation can be done. So, I know Xm, so that means I can say 2d. So, 2d will be equal to m into m multiplied by Xm. So, here actually 8 kilonewton is converted into Newton, sorry, this is not 8 kilonewton, let me m into e actually 0.156, 0.156. So, this is in Newton, this is also kilonewton. So, here actually 8 into 10 to the power 10 cube this one. So, since both are mass, so if I multiply g both sides, so it will get cancelled. So, directly W into E and this is W I have written, and here actually x m actually is 90, that is actually multiplied by 10 to the power minus 3. So, this is actually your 2D. So, if I calculate this one, 2D comes 0.156 multiplied by 1000 divided by 8 divided by no, this will be 10 to the power 6, because millimeter to it was 90 multiplied by 10 to the power minus 3 in millimeter, but if I want to meter, then it will become 10 to the power 6. So, these and this will get, so it will be there 10 to the power minus 3. So, 0.156 multiplied by 1000 0.156 multiplied by 1000 divided by 8 divided by 90, that become 0.2166 or equivalent to 21.6%. So, you can see from the peak amplitude we are getting, if I take directly from the peak using the peak amplitude, you can find out the damping, this is the way. So, it is becoming 21.6%, whereas from the other way, that means damping equal to f2 minus f1 by 2 fn, from that if I calculate, then there actually you are getting only 5%. This is actually 2D, this is actually 2D. So, your D will become 10.8% or so, 21.6 divided by 2, 21.6 divided by 2, it become 21.6 divided by 2, that become 10.8%. So, that means from the peak amplitude when you are calculating, that means from this equation we are getting 10.8%, but if you use this expression you are getting 5%. So, this is actually, this is the reason actually from the peak amplitude, if I determine the damping, it is overestimates, and whereas if I use this concept, that you get the average value of damping. So, this is better actually, but I have explained both the method, you can use any of these if there is any in the exam. So, I think I have covered enough now about the machine foundation, simple machine foundation, if rotating mass system or constant mode system, free vibration, forced vibration, and their relevant application. And then I have a very little left. So, I will give you the summary in the next class. Thank you.